Hello everyone, and welcome back to the AI Research Roundup. I'm your host, Alex. Today is May 5th, 2025. Okay, we're looking at Cross-Entropy is all you need to invert the data generating process, this ICLR conference paper published January 22nd, just over 3 months ago. This paper tackles why supervised classification, particularly using that common cross-entropy loss, leads to interpretable features, representations that are linearly decodable, meaning simple linear models can understand them. Alright, so figure 1 here illustrates a key related method called diet. It shows how diet learns identifiable features through instance discrimination, essentially telling individual samples apart. It maps samples and their augmentations close to specific cluster vectors, almost like they're sampled from those von Mises-Fisher distributions mentioned in the theory. This diet framework helps build the bridge to understanding standard supervised classification, which is central here. Okay, building on that diet framework, figure 2 here lays out a kind of family tree, a simplified genealogy for cross-entropy-based classification methods. You see how it positions diet as evolving from broader contrastive learning approaches, like GCL and TCL. And crucially, it shows standard supervised learning as a special case of diet, essentially when diet's instance labels become semantic class labels. This connection is really key for the theoretical argument. Alright, moving to the empirical side. Table 2 here gives us some concrete results from simulations focusing on that parametric instance discrimination, or PID, which diet implements. It shows how well the method actually recovers the ground truth latent variables and cluster vectors under different settings, using R-squared scores. You can see really high scores, often above 98%, especially when the setup matches their theoretical assumptions, suggesting the method works quite well in practice. Okay, so following on from the diet results, Table 3 here shows similar numerical simulations, but this time focusing directly on standard supervised learning with cross-entropy. Again, it's showing R-squared scores for how well the learned representations recover the true underlying latent variables. Well, the scores are generally very high, often above 97%, especially when the data generating process matches their theoretical assumptions, like using that VMF distribution. It even shows some robustness when assumptions are broken. Okay, so after those simulations, Figure 3 takes us to real-world data, specifically ImageNetX. It shows how well simple linear classifiers can predict various underlying image factors, things like pose or color, just by looking at the features learned by standard trained models like ResNet 50 and VIT. Well, the trained models consistently perform significantly better than chance or untrained versions, suggesting these learned features are indeed linearly decodable in practice, even on complex datasets. Okay, so following the ImageNetX results, Table 4 here dives into standard disentanglement benchmarks, the dislib datasets. It's showing Pearson correlations, basically how well the features learned by different models, like an MLP or a CNN, capture known ground truth factors, like position or scale. And you can see, particularly for the CNN features, the correlations are really quite high, often well above 0.9. This reinforces the idea that standard supervised training extracts these interpretable, linearly decodable factors. So wrapping things up, what we've seen through the theory and the various empirical results, from simulations to ImageNet and dislib, is compelling evidence that standard supervised learning, just using cross-entropy, is surprisingly powerful. It seems capable of recovering these underlying interpretable factors of variation up to a linear transformation, at least under plausible data assumptions. This really helps explain why we see things like linear representations emerge. That's all for this roundup. Thanks for tuning in.